Hi there, thanks for joining me for another episode of Code, Make, and Draw. I'm your host, Ed Cavett, and in this episode, we're going to be making some creepy spiders. To start, let's look at these spiders and see what a spider is made of. It has a random spot that it falls from, it has a random speed that it falls at, it has a random size, and when it gets back to the top, it gets a new spot and it repeats that process. To make a spider, we're going to use an ellipse for the body, the cephalothorax, an ellipse for the abdomen. We have 4 dots for the eyes and 2 lines for the fangs, and then we're dividing the legs up, so we have a front and back, left and right. So the legs are grouped so that some of them turn clockwise, some of them turn counterclockwise, and they move separately of one another so that they're not all like fanning at the same time or moving like a sine wave. Once we figured out what a spider is, we can kind of break it down into its procedures. To help with this, I've created a graphic here so we can see what parts are going to make what spider, and the different parts are made from p5.js graphic elements. We have lines and ellipses, and they're situated around the abdomen. So the abdomen is directly over the center of this object. So if you draw a spider and you rotate it, it's going to rotate around the center of its abdomen. Also, the different pieces are kind of anchored to that object's origin. So if I need to put legs on the left, those are going to be negative x values. If they're on the right, they're going to be positive x values. The same with rotating the legs. If I want to rotate legs or make them flex inward or outward, then I want to be rotating them clockwise or counterclockwise. Well, you have to be careful how you're turning these, or else you're going to have legs that are flexing in a weird direction. So I've kind of mapped those out here. We've divided the legs into front pairs and back pairs, left side and right side, and you can see how the rotation, whether it's clockwise or counterclockwise, depending on which side and which pair of legs. For the body, just move so far down and make it 1 or 2 times the size, maybe 1.75 times the size of the abdomen, and the fangs, move those up from the origin just to the edge of the abdomen, and the eyes are kind of situated with the front pair being closer together and closer to the top of the spider's face, and the back 2 eyes are further apart and further down. So that's kind of the details of how we're going to make a spider. Getting a spider shape to just move down the screen on a web line, not too complicated of a process. But if you want the legs of that spider to move, that's going to be a little bit more complicated. So to help out, I broke down the problem here so you can get a better idea of what's actually happening. So we have the whole leg pictured here. This is just one leg, and it's the front left leg. And where the joints connect, that's the center of rotation. So if I just hold on to that object and rotate it, it's going to spin at that joint. So that's kind of important to keep in mind. The very bottom, or the segment number 1, it's connected underneath the body of the spider, and it shoots out from the side, so it doesn't look like it's as big as the other segments because part of it is underneath the body of the spider. When you have that point, you just move your scale length and you draw a line. And then you translate the origin up to the end of that line, and now that's your center of rotation for the next line that you're going to draw. And you're going to draw that line a little bit shorter and a little bit thinner. So that's where you're increasing the amount that you're taking away from it. So that's your increasing factor. And you're rotating your pi times that increasing factor as well, so that the ends will move in a little bit more than the parts closer to the body. So the segment closer to the body is going to move just a little bit, and the second segment is going to move a little bit more than that, or in a range that's more than that. And then the end one is going to move in a range that's even more than that. And the reason for this is because the rotation is accumulating along the length of the leg. So if you have the first leg moving a lot, and then the second leg moving the same or more, it's just going to curl up into a ball underneath the spider, and you don't want that to happen. So you want the legs to be kind of sticking out. And you can play with these ranges to get more or less dramatic movements out of your spider's legs, but that's pretty much how the process happens. Now that we know what a spider is and how it's put together, we can start to look at it procedurally. So in p5.js, we're going to open a new sketch and we're going to start making these spiders that you see right here. This is a pretty involved program. There's all the major concepts in p5.js are involved here. If you're new to p5.js and you've studied the concepts and you're just trying to learn the procedures and maybe get a little bit more solid foothold, this might be a little bit more challenging, but I try to put enough information in here where you can, if you just type out the code or work with the code, you can download it. It's included in the description. Then you'll be able to eventually figure out what's going on and use it in lots of different ways. So that's kind of what all these annotations are for. So the very first part of the coding is in our global space, we need to declare some variables that we're going to use throughout the entire program. So we need a blank array set to the variable spider. We need a variable called shigh or spider high. How far up and down the screen is it moving? So we need a variable hold that, and then how many spiders are we going to have, and why not 13? You can have as many as you want, but just keep in mind the more spiders you have, the slower your program is probably going to run. In setup, we're going to use the available window width and window height, and then we're going to create a loop. We're going to go through the number of objects that we have in our system, and we're going to assign a new object and store it in the array variable. And when we create a new instance of an object using an array, we're going to use the variable name, the dot syntax. We're going to use the method push, and then inside the parameters push, that's what we're going to store in the array. And in this case, we're storing it in an entire object. So we're going to use the declaration new and our function name that we're going to make up, which in this case it's spider maker. And to get spiders that are more random and more unique when you have a system of them, I'm going to instantiate them using i+1. So it knows which element, which spider it's making, and then it can use some multiple to get a unique value for that spider. Lastly, we're just going to clear the background one time in setup just to be sure it's done. You might want to have some trippy spiders with some blurs, who knows. So in Draw, we're going to do some stuff with the color of the background. So I'm going to use some local variables. I'm going to set to it the return of I'm going to take cosine and sine, use frame count as an incrementer, multiply it times a decimal so I get a small incrementation each frame. And then the return of that, I'm going to interpolate that to 0 to 255, which is our color range. I'm going to do that for red, and I'm going to do that for green. And then when I declare the background color, I'm going to put those variables in there, and then for the blue, I'm going to put 75, just so I have the standard kind of color that will remain static, and that's going to create an interesting background for us. Next, we're going to loop through the spider objects. So we're going to set a loop to the length of the spider array, and we're going to loop through that as long as we're less than that length, because 0 to that number minus 1 is the number of elements in the array. Then we're going to draw a web line and the spider's body, and we're going to do the leg animation. All of that is going to be done from within this loop for each spider. So once we have that loop created, we can start doing the business inside there. We want to assign to the global variable the movement of the rising and descending spiders, and we want to translate the spider to the position and draw the web line from that origin to the bottom of the canvas. When we draw our spider, the method for drawing a spider, it's oriented face up or head toward the top of the canvas. And when spiders come down on the line, they're turned around the other way. So down is up and up is down, sort of. If you're drawing lines from that object to some place on the canvas, you have to remember this orientation. So that's going to be something that we're going to keep track of. To get the position of where the spider is and how it's moving up and down, we're going to use a sine wave. We're going to map it to a percentage of the height. So it's going to go down the canvas in appearance. It's actually moving up in numbers toward a certain percentage of the height, and it's going to go off the screen a certain percentage of the height, and that's where its position is going to change, so that we can't see the spider flickering as its position is changing. So to get the spider's position to change and its size to change, we're going to wait till it gets off the top of the canvas. So we need to look for that. So we're going to do a check for when it's off of the canvas, and we want its whole body to be off. So we can't just go by the origin of the spider's position. We have to move it a little bit further past that, so that the spider is completely hidden whenever its position changes randomly and its scale changes randomly. And that's what we do inside this condition. We're going to set the current spider's X to a random width, and we're going to set the current spider scale to a random size that's tied to the height of the screen. So if you increase the canvas size, your spiders are going to be in proportion to the canvas size. Smaller canvas, smaller spiders; larger canvas, giant spiders. And this gives you higher or lower resolution for your output. Next, we want to do a push and pop to contain any of the changes to the graphics container. And we're going to be moving spider legs and positioning eyeballs and fangs and abdomen and body. So all of these different translations we want to revert back to the original origin every time we get done doing that. So to make sure that we don't accumulate some translation and fly parts off the screen, we're going to push and pop contain any changes to the rotation, any changes to the color, stroke weight, the positions, you name it. Anything like that is going to revert back after it encounters pop. So inside that, we're going to translate to the spider's position. So we're going to look at the current spider's X. We're going to move to it. To know where its Y position is, we're going to look at that S high global variable. Once we have the origin of our spider, we can flip it 180 degrees, so now it's top down. So when it comes down the line, it's looking down, like the direction it's moving. The spiders, when they drop down, they go to 85% of the height of the screen. And when they go back up, they go past the top. And connecting them is a line, that's the web line. And that line is of a fixed length. And that length is a little bit longer than how far they are going down the screen. So it's kind of like a part of the spider, this spider silk, this line is. And it just goes up and down, and we can't see the top of it, so we can just imagine it goes away. So I just make a fixed length line and connect it to the spider, and then as the spider goes up and down, so does that line, and I never have to worry about tying that line to a side or anything anywhere. Once we have our spider spun around in the right direction and a web connecting it to the top of the canvas, we're ready to make our spider object, and we're going to do that by executing a method inside our spider object function called this.update. Also inside our spider method, our spider function, there's a method that makes the spider's body. So I took all of that work out of draw and I put it inside the spider function so that it's all kind of self-contained. And there's very little that you have to do in draw to set up how to make a spider. In fact, the setup in draw is for making the spider move up and down the screen and do things that are specific to what you want the spider to do. If you wanted it to skitter around the screen, then you would change your procedures in draw and then access the spider and set it to the origin that you get from whatever those procedures are. So you could have a completely different process out of how you set up draw and call your spider object. Before I dive into the global part of our function, the constructor part of our function, I'm going to put in all of the methods that are going to be in this function. So we have a method that does the update. That's the heavy lifting that coordinates all of the other methods, which are the right legs and the left legs, and then the spider's body, which we call from draw. So I don't think I'm accessing that method inside the function. I'm accessing that method only outside in the draw function. I could have put the spider body and just made its own function and set it off on the side wherever and then just called it. But it made more sense to make it a method inside this function so that everything is self-contained, and that way I don't have to have two separate functions to make one spider. I've got one function to make one spider, right? So when we instantiate the first spider object, we're calling the global space of this function. And inside the global space of the function, there are some initial variables here, and then there are some methods, which are variables that are set to a function. So the variables that you see here in what I call like the global space of the function, those are going to set the initial states, and then we can use those variables and make changes to them inside the methods that are contained inside this function. So for the position, the horizontal position, this.x, that's a random number, random spot. Y is going to start out fixed, and the size of the spider is going to be determined by the height of the canvas. So if you increase the canvas size, your spider is going to increase, and vice versa. Also, we have a variable that's going to hold how we shrink the length of each segment of the leg and decrease the thickness of them as we make each leg. And then where the spider is vertically, we need a variable to adjust the Y position and to give it a velocity. How fast is it going to go down? So that's all being set up in the global space of this function. The next thing in the global space of the function is the this.update method, and inside it we're coordinating how we use the other methods to return a spider to the draw function. So in the draw function we're calling this spider update method, and then it's going to construct a spider, and then when it goes back to draw, there's going to be a spider there. Inside update, we're going to advance the this.drop incrementer. We're going to either increment or decrement to go up or down the screen, and then we're going to, inside push and pop, contain all of the changes that we're going to make in order to know where a leg is, know where a body part is, to get a spider all put together. And then inside that push and pop, that's where we're doing all of the action. So we're going to start with the legs, and we kind of break the problem down into a left side and a right side, and the front legs and back legs. So to start with, we're going to do the right side legs. So we're going to give them the stroke weight set to this.sw, and then we're going to translate to the origin, that is the location of the spider. So the center of the body, and the legs are going to extend off from that center of the body. When I'm translating here, when I make small changes to the translation along the Y, I'm moving up the spider's body or down the spider's body. So I'm putting like the front pair of the legs closer to the front of the spider and the back pair of the legs closer to the back of the spider, so that they're not all setting on the same exact center point of the body of the spider. So when you see that adjustment there to the translated position, that's what's happening. Also, you can see there are some arguments that go into the parameter part whenever we call the method that makes the legs. And the first number is the number of the leg. So I want the method for making a leg just makes like one leg. It doesn't know which leg it is, front, back, left, or right. So I kind of have to tell it that. And to do that, I send into it these values. So I tell it which leg it is, 1 through 4, and it knows left or right because of the center value, which is pi, which turns the spider's leg clockwise or counterclockwise. So negative pi is a counterclockwise leg movement, positive pi is a clockwise movement, and you can multiply that times a fraction to get a lesser, like a weaker movement. So you can go from a really strong movement, and as you increment through your legs, you can get lesser movements. So maybe the front legs and the very front and very back legs move more, where the center legs move a little bit less, so that they don't kind of overlap one another or overrun one another, and you lose track of which leg is which. Is that a front leg or a back leg now? So that's kind of what those values are doing there in the parameters. Oh, and just to be clear, the last parameter represented by ln, when it's received by the function, that controls the length of the leg. So I'm going to pass into it kind of recursively the leg length, and it's going to get smaller and smaller. As this last little bit is finishing up here, you'll see that there is a lot of repetition. So again, whenever you see repetition in code, there's probably a better set of procedures, a more efficient way of doing it. And that's true, I'm sure, for a lot of this code here, but to show others how to do it and to even make it clear to myself how to do it, these are the procedures that I came up with. And I could spend a lot more time optimizing it. In fact, the version that you have here has been optimized quite a bit. You should have seen the show that this code was before, and I was able to be like, I'm duplicating this process here, I could probably double up that, I don't need this here, I can move it there. So there's a lot of that goes on. So I don't want you to look at this code and be like, yeah, that's repeating things, that's not the best idea. Well, you're right, it's not, but it's to help kind of understand the procedures if you're learning them for the first time. So that's kind of how that works when I'm designing these procedures, and it's also kind of how it works when I'm showing others. I've divided the legs in half with a right side and a left side, and I've divided them within that as the front and the back. So I'm kind of keeping things separate because their movements are separate, like I showed in the diagram at the beginning of the video. There might be a better way to do this that can blend them both together, and then you can just send in an argument that tells it the difference. But this was the way that I designed it to begin with, and it's the best that I could come up with, and also be able to share it and show it to others and explain what's going on. So each one of these leg maker functions receives some arguments in its parameters. Which leg is it? So is it a front, like leg 1, 2, 3, or 4? That's kind of the index value. That's I. So in the annotations, I refer to it as I, but it's actually arm in the parameters. That's the assignment for that argument. We're also using pi, which will be the angle that we're going to multiply, so that we can get how much rotation there is in that leg, and then how long is that leg. So whenever we call the method, we're sending into it a length, and then we're going to maybe do something to that length to make it smaller or whatever we need to do each time we make a leg. To make the legs rotate, we're going to use Perlin noise, and we're going to send into the noise part of this assignment which arm it is, which leg. I call it an arm for some reason. When I first started making this object that rotates, it was a recursive tree, and that went to a tendril, and now it's a leg. But I always kind of go back to the arm in my head. So even though it's a leg, it's an arm in my brain, and language isn't my first language. And I just noticed right now, as I'm recording the narration for the video that I've already recorded and typed in and pretty much have sealed its fate, that I used I instead of arm, and I changed horses in the middle of the race. So wherever you see I in this method, change that to arm, because I is actually supposed to be the argument that's sent into the parameter, but I switched it to arm. So you got to do that little translation there. So wherever you see I, that's going to be arm, ARM, and then it's going to receive the right variable. Now it's receiving a 0, and so if I've added it to 1, then there's a 1 there, so I'm at least getting something like 1 and not a 0, but still it's not working like it's supposed to. And I thought I noticed something, but I wasn't sure. It still kind of works. I mean, you can't really tell that it's not broken, it's just not, it's not performing the action that it's supposed to be performing, and it's doing it on the right side legs. So if you notice the right side legs were a little wonky, then that's probably why. So now that the video, I've almost have this done and recorded and narrated, and it'll be uploaded in maybe an hour, I've found out that I need to change all that. So change that. It'll be changed when I upload this to GitHub and include a link in the description below. So getting back to the video at hand, kind of getting really fatigued explaining this. Is a really long video. I just can't believe how long it is. But I think you're getting the idea of what's happening now. So I've interpolated a rotational value based on Perlin noise, and it's tied to the formulas that you see there. And then I'm moving. I have to find out what length my leg is going to be. So I need to start out with the full size scale, and then I'm going to reduce that as I go through each segment of this leg that I'm making. And I'm going to isolate any changes inside push and pop, because I'm going to be translating to the end of each segment as I move down the leg to make it. So I'm going to start at the very center of the spider, or the center of where the spider's leg is, and I'm going to rotate a little bit. Then I'm going to draw a length of line according to this dot length, and then I'm going to translate to the end of that length, rotate a little bit, shrink that line a little bit, and then I'm going to shrink its stroke weight a little bit as well, and then draw another line, and that line's going to be even smaller, and repeat that one more time for the third segment, and that's going to create your 3 segments of legs. And if you want 4 segmented legs, add another piece. And you can keep doing this. Just keep in mind that you're doing recursion. You're eventually going to run out of piece to have a segment of. So at 3 or 4, it's probably about the maximum number of segments. I think after that it starts to look like a curve, or it starts to look like a tendril. So I kept it at 3 in this example. Here you can see I'm finishing up the last segment of that leg. I've translated it to, again, this is the 3rd time, rotating it a little bit more vigorously with that 1.5 times multiplier to the radius, and the length gets a little bit shorter there as well. We're just repeating this for the other side, and I'm going to speed this part up for the sake of this video is too long already. There's not too much to talk about in this part, because it's just like the right side, except for we're flipping it over to the left, and we're doing that along the vertical axis. So it's going to be a change in the horizontal value. So we're going from positive x's to negative x's, and negatives to positive. I think they're going all positive to negative. So let me try to follow along here and see where they stick out. So I think here those stay the same. Right in here, I think the line, yeah, it's negative this dot length. We're translating to negative this dot length on the x, and yep, translating to negative this dot. So you can see how that has changed from the right side. When we translated, we did positive, or I think it was just a 0 value, wasn't it? Oh yeah, it was a positive length, and here it is a negative length. And then we draw the line, we just use a negative length again. And that's going to flip everything over. Once we have the legs, we're ready to put the body on top of that, so we can access the spider's body method next. And I think that's what we do in the update. We access the legs, now we access the body. And the output for the body is going to be on top of it, and it's going to hide how the legs are kind of weirdly connected at the center. The spider body method receives a value which tells it which spider it's on, so it's getting that index value, and we need that so we know which spider's body we're making, because not all spiders are the same size in this output. So we're going to set a local variable equal to the current spider's size, and its abdomen is bigger than its body, and its legs are fractions of the body size. So the body is like 1 unit size of the spider, and then anything on the spider that's not the body is going to be proportional to that unit value. So that's why it's exactly the scale. And then when we make the abdomen, we're going to go a little bit larger. So when we draw the ellipse for the body, it's going to be its scale size, and we're going to shrink it along the horizontal axis. So the width of the spider's body is going to go inward, while its length is going to stay the same. And we're going to do the sort of the same thing for the abdomen, but not as much. So it's going to be a little bit elongated, but not too noticeably. Just enough so that it's not perfectly round like a grape, but a little bit stretched out. You know how like spiders' bodies are. To make all this proportioning easier, because we're going to be putting on fangs and eyeballs, and they're going to be situated from the center origin by so far. Like, I don't want it to be all the way off of the spider, so it has to be within the scale distance of the spider, that unit size. So we're going to be multiplying that unit size times fractions all over the place. So to make it easier, I just set some local variables to some values that I thought would work best, and you can tweak the size of your spider by adjusting those variables instead of going in and have to hard code everything, because we use these again and again and again. You can see when I make the ellipse, I'm using the body size 1 and 2 there, and then 2 and 3 for the abdomen part. Same with the fangs. When I get to the fangs here, I'm going to set the local variables equal to different locations. So I have a left and right fang location, and then where the start of the fang is and the end of the fang as it sticks off of the face. I need those locations. And those are going to be fractions of the size of the spider added to or subtracted from the origin of the spider. So everything is kind of in proportion. We're drawing lines for fangs, and we're going to use the size of the spider, that local variable size, and we're going to multiply it times those factors, and that's going to give us the length of the line. And then if it needs to be a fang on the left-hand side, well, then it's going to have negative numbers, and if it's a fang on the right-hand side, it's going to have positive numbers. So that's how you kind of situate the coordinates for the fangs. The same with the eyes. We have 2 pairs of eyes, so 4 eyeballs. We got a pair in front, a pair in back, and there's a, like the left side and the right side. So I did I think the right fang first. Or no, left fang first, and then the right fang. I annotated it up there because I knew I would forget. So you can see from the negatives and the positives given to size times fang, whatever value, which fang it is. So you can see how the mirroring the values is just a matter of changing them from positive to negatives, which when you're dealing with making objects that are symmetrical, this is really handy, and why you want to build your object so that it has a 0, 0 origin, because the reflection is going to be the same number values, just a negative. So it makes things a lot easier with the math. You don't have to do all the computations. So that's why we kind of build things that way, and that's why the translate and the push and the pop are so handy when it comes to building these kind of objects. So with the eyes, it was a little bit trickier because you don't have a lot of space. You can see I'm dealing with really small changes in the numbers here. And since my spider's body is a lot narrower than it is long, that the distance between the eyes is really small, so you have to keep that in mind too. If you make a spider with a really wide body, the eyes are going to be positioned as if it's a narrow body, and that may not work as well. So kind of play around with those and adjust the location positions here. You can play around with these values just to get a feel with how the eyes are laid down on the body, in case it was kind of confusing. So I'm going to lay these points out, and those values probably aren't going to make any sense to you because they're coordinated to the local variables, so it's kind of hard to remember what i's d3 is versus i's d4. So looking at the point coordinates is not really helpful in this. So I would just recommend copying the code and then playing around with it so you can get an idea of what's really happening there. I mean, I could explain it to you all day, but until you really get your hands on it and mess around with it, it's not going to make as much sense. In spite of that, I still kind of add this annotation here where it tells you how the polarity of each one of the coordinates in the 4 points is supposed to go. So in point 1, it's a negative number and a negative number. In point 2, it's a positive number, negative number, then negative, negative, positive, negative. You can see how it kind of goes there. So that's it pretty much, kind of. I'm going to scroll up to the top and I'm going to press play, and then I'm going to see that half the legs are missing. So if I turn the spider around, it's the left hand side of the legs. So find that part here, and what's really amazing about this is as I'm looking for the mistake, I don't find the most obvious one, which I found first thing when I was going through the video here doing the narration, but I didn't find when I was looking straight at it trying to find the mistake. I didn't notice that arm in the parameters is being used as I in the actual method, so I need to take that I out of there and put arm in there, but I don't do that. Instead, I think about the mistake, I look down here and I find a value that's off. So it just goes to show how one tiny mistake can make a big difference here. I had an extra 0 there and it made the legs so small you couldn't see them. So now that the legs are big enough to see, everything looks pretty cool. And since the arm and I that mix up there, all it's doing is it's just returning a 0. It's giving a 0 value for there, which is actually a valid return, or a valid number for that, a valid argument, except for it's supposed to change. It's not supposed to say 0. It's supposed to change over time in order to make the legs move differently, but it's not making a huge difference in the output. But if I looked at it closely enough, I could tell that it is. So I'm going to change that code, and when I upload it, you'll have the fixed version with that changed in here. Or if you're typing along, just change that now and it will be fixed. So I'm going to take all the annotations out of here so you can see how this code looks without all of the extra messy stuff explaining what it is. Now there'll be some of the extras hanging on the side there, but that's okay. So there is quite a lot to this, but like I said, some of this repeats itself and you don't necessarily have to do this. Like I don't need 2 methods for the one method for the right or one method for the left side. I can combine that into one method. But for the sake of being able to show things a little bit easier, I decided to split it up. And it also made it easier when I was designing things, because now I know I can combine it into one method, but I may not have realized that before doing this. So sometimes it's helpful to start out that way and then just optimize it once you've figured things out really solidly. That's the end of the video, and you're still here? Well, hit thumbs up. Reward yourself with a thumbs up. You deserve one. Hit that thumbs up for yourself. And hit subscribe if you haven't and you want more content like this. Hit the bell to be notified, and tell me what you think. Let me know. Give me some feedback. Did this help you? Did it not? Is there something that you'd like to see differently? I'd love to hear what your thoughts are. If you make a version of this, please share it with me on my social media. I'd love to see that as well. I guess that's it for this one, and as always, until next time, take care.